Hello everybody, in this video we are going to look at the death of high mass stars. The low mass stars went out in a beautiful planetary nebula transitioning to a white dwarf. Our high mass stars, however, are going to go out with a bang, one of the biggest explosions that's possible in the universe, a supernova explosion. So let's look at how a high mass star dies and why it dies in this incredibly powerful explosion known as a supernova, which leaves behind these things called supernova remnants, which you can see here as the Crab Nebula, a type of emission nebula created by the explosion of a star, a high mass star. Okay, if we're going to get to the death of the high mass star as a supernova, we have some work to do. We have to understand what's going to happen that's different in the core of a high mass star compared to the low mass star. Remember, the low mass star, we fuse elements all the way up to carbon with a little bit of oxygen mixed in, but we never reach the critical temperature, the next fusion ignition temperature of about 600 million Kelvin to begin fusing carbon into heavier elements. Stars that have mass of about 8 times the mass of the sun, you know that dividing line that we drew between high mass stars and low mass stars? Stars that are greater than 8 solar masses, or what we'd just call high mass stars, have enough mass so that the cores of those stars will reach the fusion ignition temperature to fuse carbon into heavier elements. They will hit 600 million Kelvin. They will ignite carbon to neon fusion in the cores of the stars. It can take a few different routes. The most popular route is to fuse carbon into neon, but you can also get carbon into sodium, and less frequently you can get carbon into magnesium. That's details that I'm not really concerned with you. I'm not really concerned that you remember. I'm more concerned that you remember that high mass stars reach the fusion ignition temperature to start a round of carbon fusion. And the fusion is going to keep on continuing as well. We're not going to stop at just fusing carbon into neon. These stars have enough mass to hit every subsequent fusion ignition temperature. It will go all the way until you essentially cannot get energy from fusion anymore. The end of the line, the dead end of fusion. And this happens when you fuse iron. So we are going to proceed to fuse elements in the core of these high mass stars, past carbon, past neon, all the way up to iron. And once we hit iron, we're going to see that that's going to mark the death of a high mass star. But in general, we're going to keep doing these rounds of fusion. It's going to be just like we saw in our low mass stars, where we started with hydrogen to helium fusion, built up a helium ash core. Then we started helium to carbon fusion and built up a carbon ash core. Now we're going to do carbon to neon fusion, building a neon ash core. Then we'll do neon to heavier stuff, fusion, building up a new ash core, building up a new ash core, all the way through several cycles, building up a new ash core with new fusion shells each and every time. And at each step of the way, we'll build up a new ash core, reach a new fusion ignition temperature to fuse to a heavier element. And each time we start a new round of fusion, we add another shell to our core. So we're going to end up with this really complex onion shell sort of structure for our high mass star. And we're going to keep adding new ash cores and then subsequently new layers of fusion, new shells of fusion, all the way up until we hit this iron ash core. And just to be clear about this one, you're going to see Fe a lot. Fe is the elemental symbol for iron. I know it's a little bit strange, but it's for the Latin word for iron. So iron is Fe. So with each one of these, it's build up a new ash core, hit the fusion ignition temperature, start a new round of fusion to heavier elements, which adds another shell of fusion, and then do the process over and over and over and over again. And at the very end, at the near death of the star, we're going to have a very onion shell-like core, because each new round of fusion builds a new shell of fusion. And this is actually going to proceed fairly rapidly. I don't want you to memorize the numbers that I have here, but I am going to talk through them. But before we actually go all the way up to carbon fusion, well, actually, let's just go ahead and jump into the list. Let's consider a 20 solar mass star. Clearly enough mass to go through all of the fusion stages to build up this iron ash core, which will be the death of the star because you can't fuse iron into anything heavier. Iron is the end of fusion, and I'll get back to that here in a minute. But uh, in a 20 solar mass star, you live the main sequence life. That would be the hydrogen to helium burning, and that takes about 10 million years. Then you do helium to carbon fusion, and that cycle doesn't last very long, only about 1 million years. And then you'd have your carbon burning phase where you have core in the very central part of the core. You're fusing carbon into heavier elements. So then you'd have carbon burning that would last about 1,000 years, which makes carbon to oxygen, neon, sodium, and magnesium. Then you do neon burning. The neon fusion stage only lasts about a year. Remember, we're talking about 1 year. You've all been alive for several of these years. And this is an entire fusion stage near the very end of a star or of a high mass star. So these very last rounds of fusion occur very, very, very rapidly. The oxygen fusion stage, only a couple of months. And then the last round of fusion is silicon fusion into iron. And this only lasts days. I spent days making these videos, and during that time, a high mass star like Betelgeuse could have started its silicon to iron fusion and already gone supernova. So once that starts, it's a very, very rapid process. So right at the very end of the life of a high mass star, right before it's going to go supernova, we have this very onion shell-like core. Now I want to be clear that the core at this point is really, really small, compact, and tiny, super duper dense. And then you're dealing with an absolutely giant envelope around the star. So the core is really, really, really kind of small. The whole star is huge, about 500 times the size of the sun, but the core is only about the size of Earth. And in that core, the very center, you have your iron ash core. Then you have a silicon fusion shell, magnesium fusion shell, neon fusion shell, oxygen fusion shell, carbon fusion shell, helium fusion shell, hydrogen fusion shell, and then you have your envelope, a very onion shell-like thing. And each one, the hydrogen is making more helium, feeding into that shell. The helium is making more carbon. The carbon is making more oxygen, so on and so forth. You definitely don't need to memorize those, but you should know that we have an iron ash core and several layers of fusion shells. Now let's talk about why iron is the end. So before zooming in, let's consider what's going on with this iron ash core. We've been continuing new rounds of fusion, because remember, in a fusion reaction, you're taking two lighter nuclei, fusing them together to make one heavier nucleus. And in that process, a little bit of mass was lost and converted to energy using Einstein's E equals mc squared, the mass energy equivalence principle. But if you look at the atomic structure and beyond the scope of this course, but iron ends up being, out of all the elements on the periodic table, it has the lowest mass per nuclear particle. So if you're looking at the overall mass of iron per nuclear particle, so a nuclear particle being a proton or a neutron, iron has the lowest mass per nuclear particle. And what this effectively means is that if you were to fuse two iron atoms together, you wouldn't end up with something with less mass, you'd end up with something with more mass, because the resulting nucleus would have more mass per nuclear particle. And in that case, that would require energy. If you're not losing mass and converting it to energy, if instead you're creating mass, really, you're sucking up energy to turn into mass, then that's not going to release energy. It's going to require energy to make that fusion reaction happen. And the way that nature works is it doesn't do that. We will only fuse things if you're going to get energy out. So you're not going to fuse iron into anything heavier. It just comes down to the fundamental atomic nature of iron itself. You can't fuse iron and get any energy out of it. And then everything past iron follows that same sort of rule, which is why whenever we talk about fission processes, we use heavier elements and break them into lighter elements. And you can do that. You can fission and get energy out all the way down to iron. You can fuse and get energy out all the way up to iron. Iron is the bottom point of where you can actually get energy from either fusion or fission. The short of it all, and what I'd like you to remember, is you cannot get energy from iron fusion, so iron fusion doesn't happen. It is the end point for fusion, and therefore it is going to be the end of energy production for this star. And that is going to doom this iron ash core, which is rapidly growing because the fusion reactions are super duper fast and all the silicon is rapidly becoming iron. So pretty much the entire core is rapidly becoming an iron ash core. And with no fusion to ever support it and more mass getting packed on top of it, something is about to break. And I want to go ahead and really emphasize what is about to happen to set the stage, because the key point is, regardless of how much mass gets packed on, how tightly we squeeze the iron ash core to jack up the temperatures, you will never do another round of fusion. Fusion just will not happen. So we can't play the game of reach a new fusion ignition temperature. Something else is going to have to happen. So iron is the endpoint of fusion. And now this is going to mark, as soon as that iron ash core pretty much appears, you have days until there's a catastrophe in the core of the star, because you're still creating more and more mass in this non-fusing iron ash core. It's going to just get more and more and more massive. It's going to become electron degenerate. So why is this? What is supporting this iron core from this? As the mass of the core goes up, as it gets more and more dense, then gravity is going to be squeezing it together tighter and tighter and tighter. What is the only thing keeping it from collapsing? There'll never be fusion to give the thermal pressure required to offset that. Well, we have our electron degeneracy pressure, the fact that you can't squeeze electrons really close to one another due to the Pauli exclusion principle, due to quantum mechanics. So this iron ash core is supported from further collapse. It fights off gravity by electron degeneracy pressure. The problem is, electron degeneracy pressure is not infinitely strong. Gravity is getting stronger and stronger and stronger, and eventually gravity will become strong enough to overcome electron degeneracy pressure. The gravitational force will go past the limits of what electron degeneracy pressure can do. So as the mass keeps going up, eventually gravity will become stronger than electron degeneracy pressure, and that's going to cause the core to collapse. And when we do something that sounds absurd, like overcoming electron degeneracy pressure, we are going to see an amazing process happen. Because once you overcome that electron degeneracy pressure, you are doing something fundamentally different to what's going on with the atoms. In fact, you're about to destroy pretty much everything that you fused. Because the second that the gravity overcomes electron degeneracy pressure, then the core is going to start to collapse. And then over the course of just a few milliseconds, two events are going to happen that are going to result in a supernova explosion. So over a course of a few milliseconds, the first thing that happens is what we call photodisintegration. So now that electron degeneracy pressure has been overcome, the core is going to start collapsing. Those temperatures are going to skyrocket in the core. They're going to rise to over 10 billion Kelvin. And if you think about a black body that has a temperature of 10 billion Kelvin, that's going to have its peak in very, very, very short wavelengths. In fact, something that has a temperature of 10 billion Kelvin is going to produce an enormous amount of very high energy photons, gamma rays. And these gamma rays, each individual photon will have enough energy, more energy than the binding energy of the atom itself. So if one of those gamma rays hits an atom, it blows the atom up. Maybe not blows it up is the right way to say, but it'll rip it apart. We call this process of a photon, a gamma ray that has enough energy to break apart the nucleus of an atom. We call that photodisintegration. So as soon as that core starts to collapse and the temperatures skyrocket past 10 billion, you start producing a lot of these, or 10 billion Kelvin, you start producing all of these gamma rays. All of these iron atoms that are making up this core are going to get photodisintegrated. They're going to get ripped apart and turn into helium nuclei, protons, and free neutrons, mostly helium nuclei and free neutrons. All of that iron that we spent all that time building up, and all those other heavier elements we spent time building up, are now just a large amount of them are going to get ripped apart by photodisintegration. And photodisintegration, remember that we're taking heavier nuclei now, like iron, and splitting it into lighter nuclei. The lighter nuclei have more mass than the heavier nucleus. This is a fission reaction of taking a heavy thing and splitting it apart. And since these we're splitting it into things lighter than iron, this requires energy. So once photodisintegration happens, not only do we have the gamma rays that are breaking apart the iron nuclei and every other nucleus it pretty much encounters, but it is also sucking energy out of the core, which means that it's taking away any possible energies that could fight off gravity, which is going to cause the core to collapse in relative free fall. It's going to reach speeds of a few tens of % of the speed of light. But that's not the only thing that's going on. We'll get back to the collapse part, because now the collapse is still happening. We're losing the iron. We're photodisintegrating all the iron. We're ripping apart the nuclei, turning them into helium atoms, alpha particles, and neutrons. But eventually, we're going to squeeze everything together, because gravity is compressing everything to an incredibly high density where the electrons will combine with the protons of the helium nuclei. We will squeeze the electrons into the nucleus. We'll have a positive nucleus, the proton in the nucleus, and the negatively charged electron merging together. This results in the creation of a neutron and a neutrino. So, because the densities get so high, the electrons get squeezed together with the protons in a process that we call neutronization, where basically you're converting the proton and the electron, you're turning them into a neutron, and you're creating a neutrino. Remember, neutrinos don't really interact with anything. You need like a light year of lead just to stop, have a 50% chance of stopping one. So they just boo right out of the star, right out of the core of the star. They get the heck out of Dodge. But they carry some energy with them whenever they do that. So we photodisintegrate, rip apart all of the iron nuclei, creating helium nuclei and neutrons. And eventually the densities get high enough where we get rid of the helium nuclei, because we're literally combining the protons and the electrons together via a process called neutronization to create a bunch of neutrons and a bunch of neutrinos. This does not sound like it's going to go well for the star, because with no pressure to fight off gravity, we've overcome electron degeneracy pressure. And we're actually sucking energy out by this photodisintegration, this fission process that requires energy to force it to happen. Then there's nothing really resisting the collapse of this core. So it experiences free fall collapse. Free fall collapse, just like if I just drop this, there's nothing really slowing down the fall, so it just falls according to gravity. And during all this, we're going to get the neutronization happening, that's converting pretty much every bit of the core material, or the vast majority of it, into neutrons. So we're essentially turning the core into this super extremely dense ball of neutrons that has densities, and I list them there, of 100 million billion kilograms per cubic meter. So cubic meter, boop, boop, draw a box, fill it with this core material, this ball of neutrons that we're making, and there would be 100 million billion kilograms in a cubic meter. Well, that's a lot. Another way to put this is a teaspoon of this material would weigh about as much as a mountain. It would weigh about 10 billion tons. That is some extremely dense stuff. In fact, it's the densest stuff in the universe. So we're creating this dense ball of neutrons. But like electrons, in a similar sort of way, neutrons also resist getting squeezed together. You can't make two neutrons occupy the same volume. Quantum mechanics says no. So just like we had electron degeneracy pressure, we also have neutron degeneracy pressure. And as we're making this ball of neutrons and squeezing them together, eventually we're going to hit this neutron degeneracy pressure where these neutrons refuse to be squeezed together anymore. However, we're dealing with a whole lot of mass over uh, or about one and a half solar masses or greater that's in free fall collapse. And whenever you can work out all the physics of that, that means that this core is collapsing at about 25% of the speed of light at 70,000 kilometers per second. That's incredibly fast. And remember, it's only traveling the size of an Earth, so this is why it's only taking milliseconds. That happens very, very, very rapidly. And it's going to hit this new resistance to gravity, which is strong enough to fight off gravity, neutron degeneracy pressure, but it's going to hit it like a hard wall. And just like I felt the table push back and that energy went into and through my fist, that's going to happen whenever neutron degeneracy pressure is hit. That's going to create a rebound of energy back out into the star, except it's not even like whenever I hit the table. I'd have to hit the table supersonically hard to create the shock wave. That would create a shock wave. And now that shock wave of this dense ball of neutrons coming together, hitting this hard wall of neutron degeneracy pressure, will send out a shock wave reverberating throughout the star, which canonically, that will blow up the star in what we call a supernova explosion. This type of supernova explosion, where we are blowing up a high mass star by collapsing the core, we call such supernovae core collapse supernova because we are creative. They are also called type 2 supernovae, where type 2 supernovae, where we come up with that naming convention just through observations of supernova. So we saw there are basically two different kinds of supernova going on, type 1 and type 2. We're looking at how they brighten and how they fade in brightness over time. And it turns out that these type 2 supernovae are the core collapse ones, the death of high mass stars. Now notice I have this little green asterisk right here. If you go to the unit notes, unit slides, I have a little bit more information on this. This is the sort of canonical view. But over the past decade or so, we're moving away from this idea that you hit this wall of neutron degeneracy pressure and then that sends out a shock wave that blows the star apart. Yes, that all happens, except it looks like the energy gets caught up in the star itself. So just this rebounding shock wave doesn't have enough, it's not enough to blow up the star. So the emerging view is we forgot about all those neutrinos and we forget about how much star material is there, and it's pretty darn dense. So not only do you have this reverberating shock wave that's trying to blow the star apart, but you're also sending out a boatload of energy streaming out through the star in neutrinos. And sure, almost every single one of them makes it out of the star without interacting with everything, but not all of them. And you're creating a unimaginably large number of them. So enough of them interact with the material in the star to dump their energy into the star. And that, plus the rebounding shock wave, does provide the energy to make the star go boom. So there we did it. We blew up a star in a supernova explosion, a high mass star, an 8 times the mass of the sun or greater star. And these supernovae are some of the most energetic events in the entire universe. A supernova will release roughly about 10 to the 44 joules of energy, which is just a big number, like a really, 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 really big number. Put that in context, over the 10 billion years that our sun will be sending out energy into the universe on the main sequence, over all 10 billion years, it will cumulatively have released about 10 to the 44 joules of energy. So we're talking about all the energy that the sun will release in its lifetime happening in a blink, in a single event of a supernova explosion. Another way to think about it is that amount of energy makes a supernova that's going to be happening. We most commonly observe them happening in other galaxies. And the supernova, whenever it happens, shines as brightly as the galaxy it's exploding in. I mean, think about it. It's shining with the light of about 10 billion suns, or it's shining with light of billions of suns, hundreds of billions of suns. How many stars are in a galaxy? Tens of hundreds of billions. And that's just the energy that's being released as light, as electromagnetic radiation. We also have all the energy of the neutrinos, which is carrying off about 100 times more, 10 to the 46 joules of energy. That is an incredibly large amount of energy. What gets left over? We built this ball, this dense ball of neutrons. How big is it? It's collapsed down to about 20 kilometers in diameter, 10 kilometers in radius, the size of a small city, like the size of Manhattan. But it contains about 1.5 to 3 times the mass of the sun. And something that's the size of Manhattan, or at least spherical. And it's made out of neutrons. What could we possibly call this dense ball of neutrons in outer space? Oh, we just made a neutron star. This is where neutron stars come from. They're the remnant of a type 2 supernova. They're the remnant of a core collapse supernova. However, if the mass of the original star, the progenitor star, is about 25 times the mass of the sun or greater, then whenever you're going through that core collapse process, neutron degeneracy pressure is not enough to fight off gravity. And once you go past neutron degeneracy pressure, as far as we know, as far as our physics has developed, there is no known force left to fight off gravity. So with no other force that could ever fight off gravity, we go with I guess that means it collapses down to a single point and you form a black hole. We know it forms a black hole. Whether it collapses down to a single point, a singularity, is a topic for another video. Some people say yes, some people say no. But in either case, a black hole will be formed in that scenario. So the death of a high mass star, 8 to 25 masses, results in a supernova explosion that forms a neutron star. 25 solar masses or greater results in a supernova explosion and the formation of a black hole. All right, some really, really exciting stuff. We're blowing up stars and stuff like that. Don't worry, we're not done blowing up stars. We're going to blow up a different kind of star. We're actually going to blow up a white dwarf next. It's going to be an entirely different process. But yeah, we can blow those up too. All right, let's continue our cosmic explosions in the next video.